Hello everyone. Today I want to talk about a topic that really confused me when I first saw it in a communication systems course. That is, the idea of group delay and phase delay. First off, I would like to point out that this is not a video that rigorously proves the formulas for the group delay and phase delay. Rather, I want to use a very simple example to illustrate how a signal behaves when it passes through a typical communication channel. And through this illustration, hopefully you will understand how the phase response of a system affects the input signal. Now, I think we should start by setting up our problem. We have a communication channel, or filter. We send in a signal, let's say m of t cosine 2 pi of ct. Now, what kind of a signal can we expect from the output? Well, the output signal should have the following form. I know this looks a bit complicated, but all you need to expect is that in general we will have two delay terms, namely tau sub g in the m of t term, which we will refer to as the group delay, and tau sub p in the cosine term, referred to as the phase delay. I know I'm skipping a lot of details here, but the purpose of this video is not to go too deep on why we would send such a signal through a channel, but to show how the channel affects the signal such that these delay terms are introduced. In other words, what are tau sub g and tau sub p? Now, before we begin, we have to spend a few minutes on some prerequisite knowledge. Number one, we have some basic trigonometry that I think might be worth pointing out. I'm not going to prove it, but we will use it later in this video. Number two, if we have a pure cosine wave, what does its Fourier transform look like? Well, it should look something like this, which are two scaled delta functions at the positive and negative frequency of the signal. I know these are quite basic, so I'll just go through these briefly. Number 3. Properties of convolution. First, we have the convolution theorem, which states that if we convolve two signals in the time domain, we are actually doing multiplication in the frequency domain. Second, if we want a more visual way of understanding what convolution does, here's an example. We have our signal, and if we convolve it with this particular signal, in this case it's the Fourier transform of a cosine wave, we will get something like this, which are two rescaled versions of our original signal replicated at the positions of the two delta functions. Number 4. We have some basic signals and systems we need to cover. Suppose we have a linear time invariant system with impulse response h of t and frequency response capital H of f. If we send in a signal xt, the output will be the convolution of our input signal and the system's impulse response. And from the convolution theorem, we can say that the Fourier transform of the output is the Fourier transform of the input times the system's frequency response. And since these are all complex numbers, the magnitude and phase of the output should look something like this. For number 5, we have a specific property of the Fourier transform, that is, the shift theorem. Namely, if we have a signal c of t with a corresponding Fourier transform, capital C of f, then the Fourier transform of c of t minus t0 is equal to capital C of f times this particular complex exponential term. Here we have an example to illustrate what's going on. We know that sine 2 pi fct is equal to cosine 2 pi fct minus pi over 2, and we can factor out the 2 pi fc to get this last thing right here. And by the shift theorem, we can say the corresponding Fourier transform is this thing below. Notice that the t0 term from above is equal to the pi over 2 over 2 pi fc term here. Now, let's take a closer look at what this capital C prime of f means. If we let f be equal to fc, then capital C prime of fc will be equal to the original capital C of fc times this negative 90 degrees phase term. Similarly, for f equal to negative fc, we will get a plus 90 degrees phase term. The picture should look something like this. For those of you who are not that familiar with this kind of interpretation of the shift theorem, I think it is quite worth your time to pause for a moment and try visualizing this yourself, we will be using a lot of these types of visualizations later on in this video. Now, let's look at another example. Suppose we have a signal m of t equals 1 plus 1 over 2 cosine 2 pi t plus 1 over 4 cosine 4 pi t. What does the spectrum of m of t minus 1 over 12 look like? Now, the original spectrum should look something like this. And if you apply the shift theorem properly, you should get something like this. M prime of f is equal to m of f times exponential negative j f pi over 6. Now, what does this m prime of f look like? If you are familiar with my previous example, the visualization in your mind should look something like this. I've listed out the values of the spectrum at frequencies 0, 1, and 2 for your reference. We can see that we need a negative 30 degrees phase term for m of 1 and negative 60 degrees phase term for m of 2. Now we can finally talk about our main topic. Let's first start with the phase delay. Again, we have our channel and our input signal and our output signal. Now our focus will be on the tau sub p term. Suppose we let our m of t be exactly equal to the example shown earlier, and our channel has the frequency response shown here. What will happen to this signal when it passes through? Well, first recall that in our original setup, we didn't just send in m of t. We sent m of t times cosine 2 pi of ct. Therefore, from prerequisite knowledge numbers 2 and 3, our input signal should look something like this. Now we passed this through our communication channel. What can we expect from the output? Recall that the system has this particular frequency response, and I encourage you to pause this video and try visualizing it yourself. We can see that the magnitude is equal to 1 for all frequencies. Therefore, the arrows should not change in length. But the phase response says that we need a negative 90 degrees phase term for all positive frequency components, and a plus 90 degrees phase term for all negative frequency components. So the result should look something like this. Now, for those of you who are very familiar with all the prerequisite knowledge I mentioned previously, you should be able to recognize that this result we just obtained is exactly capital M of f convolved with the Fourier transform of sine 2 pi of ct. Therefore, our output signal is m of t times sine 2 pi of ct, which we can reform into something like this. Now, recall that we said the output of the communication channel should have the form m of t minus tau sub g times cosine 2 pi of ct minus tau sub p, as shown here. We can obviously see that the tau sub p here is equal to pi over 2 over 2 pi of c. And since pi over 2 is equal to the negative of the phase of h of fc, we can write tau sub p in the following form. And there you have it. We now have our formula for the phase delay. I know that some people might find it weird that I concluded that this is the formula for the phase delay by only showing one particularly designed example. And I know that just because the phase value of h of fc happens to be equal to negative pi over 2, we cannot conclude the general formula for the phase delay. But as I said before, this is not a rigorous math-proof video. My goal here is to illustrate how the signals and the formulas come together. And honestly, sometimes it's more satisfying to see a formula actually match a result from a simple example. Now, we move on to the group delay, which is a bit harder to visualize than the phase delay. Again, we have our system and our signal, but now we have a channel whose phase response has a slope of negative pi over 6 for both positive and negative frequencies, and the phase response at the frequency fc has the value negative pi over 2. What would the output signal look like? Just as we did for the phase delay, m of t times cosine 2 pi of ct is the signal we are sending in. But this time, the channel is much more complicated. If you need a minute, feel free to pause the video and think what the output should look like. The result should look something like this. the number above each dashed line represents the phase term for each arrow. Now, we know that the output will have this particular form, and we also know that the tau sub p here is equal to pi over 2 over 2 pi of c for this particular example. Recall our phase delay formula from earlier. So our output is actually m of t minus tau sub g times sine 2 pi fct. Now, how do we get the tau sub g term? Here's a trick. We pass the output into another system that first multiplies the signal by 2 times sine 2 pi fct and then low-pass filters the signal. Now I know that this is slightly harder to visualize, perhaps the most difficult visualization by far. But for this one, I will leave it to you to go through each visualization step by yourself. I will just show you the final result. So this is what the final spectrum should look like, which is actually the spectrum of m of t minus tau sub g. If you're not convinced, then here's a quick explanation. We multiply the signal by 2 times sine 2 pi fct, and from prerequisite knowledge number 1, we can say that this is equal to this. And after canceling and combining some terms, we get this. Passing it through a low-pass filter removes the cosine 4 pi fct term, and finally we are left with m of t minus tau sub g. Now, doesn't this look really familiar? It is exactly our example from prerequisite knowledge number 5. Therefore, we know that we are going to use the shift theorem to finally bring out the formula for tau sub g. By the shift theorem, we can say that the Fourier transform of m of t minus tau sub g is capital M of f times exponential negative j 2 pi f tau sub g. And from our example from prerequisite knowledge number 5, we can know that 2 pi tau sub g is equal to pi over 6. But recall that pi over 6 is equal to the negative of the slope of the phase response. So we can say that 2 pi tau sub g is the negative of the derivative of the phase response with respect to f at fc. And finally, we have tau sub g is equal to this thing right here. Note that this also applies to the continuous case where the spectrum is continuous in f. And there you have it. We have our formulas for the group delay and phase delay. Normally, I think most professors won't accept this as a proof if this were on an exam, because you cannot use this example to claim that this works for all cases. And yes, I did skip some assumptions, such as the ones down here, but I hope that the main takeaway here is that you know how signal processing actually looks like. And maybe next time someone asks you, what is the group delay and phase delay? You will be able to provide them with not just a rigorous proof, but also a more visual explanation.